Our topic is Booth's algorithm. Introduction. Booth's algorithm is a multiplication algorithm used in computer arithmetic to multiply two binary numbers. It was developed by Andrew Donald Booth in 1950. It is widely used in modern processors for efficient multiplication operations. This approach uses fewer additions and subtractions than more straightforward algorithms.
The binary frame. Binary multiplication is a process of multiplying two binary numbers which consist of only 0 and 1 using the rules of binary arithmetic. It is similar to decimal multiplication but with only two possible digits 0 and 1 instead of 10, 0 to 9. Binary multiplication involves bitwise and or and shift operation to perform multiplications of the individual bits. The next how to improvisation of the Booth algorithms. Traditional binary multiplication methods are based on the long multiplication technique which involves shifting and addition required. Long multiplication can be slow and inefficient for especially for the large binary numbers as it requires multiplication and shift for each byte of multiplier. Booth algorithm was developed to improve the shift of binary multiplication by reducing the number of shifts and additions required.
Hello everyone, my name is Ayush Ladha and today I will be explaining you the flowchart of the Booth's algorithm. First of all, Booth's algorithm is a multiplication algorithm that is used to multiply two binary numbers. It is particularly useful for hardware implementation of multiplication since it requires only binary additions, subtractions and shifts which can be implemented efficiently in hardware. The flowchart of the Booth's algorithm is as follows. In the first step, the algorithm starts by initializing the multiplicand, multiplier and the accumulator. The multiplicand and the multiplier are the two binary numbers to be multiplied and the accumulator is initially set to 0. The counter is also initialized to the number of bits in the multiplier. This is used to keep track of how many times we need to iterate through the algorithm. Then in third step we check the least significant bit of the multiplier. If it is 1, we add the multiplicand to the accumulator using 2's complement arithmetic. If it is 0, we skip this step. Then fourth, we right shift the accumulator and multiplier by 1 bit position. This is equivalent to dividing the accumulator by 2 and shifting the bits in the multiplier 1 position to the right. In the fifth step, we decrement the counter and if it is not 0, we go back to the step 3 to repeat the process for the next bit in the multiplier. And in the last step, when the counter reaches the 0, we have completed the multiplication and the product is stored in the accumulator. Overall, Booth's algorithm is an efficient method for multiplying the two binary numbers, especially when implemented in hardware. This flowchart helps to visualize the step involved in the algorithm and how each step contributes to the final result. Thank you.
Working of Booth's algorithm. Booth's algorithm is a signed digit algorithm, which means it can handle both positive and negative binary numbers. It uses a technique called Booth encoding to convert the multiplier into a series of positive or negative numbers depending on the value of the current bit and the adjacent bit. Booth's algorithm performs multiplication in two main steps: the Booth encoding step and the partial product accumulation. Booth encoding step. In the Booth encoding step, the multiplier is scanned from right to left and each pair of the adjacent bits is examined. If the pair is 1 0, it is replaced with 0 1, and if the pair is 0 1, it is replaced with 1 0, and a positive or negative multiple of the multiplicand is added to the result. If the pair is 0 0 or 1 1, no operation is performed. This encoding process reduces the number of non-zero bits in the multiplier, which in turn reduces the number of shifts and additions required in the next step.
In the partial product accumulation step, the encoded multiplier is used to determine the number of shifts and additions required. Starting from the leftmost bit of the encoded multiplier, if the bit is 0, the multiplicand is shifted to the left and no addition is performed. If the bit is 1, the multiplicand and its negation are added together and the result is shifted to the left. This process is repeated for all bits of the encoded multiplier accumulating the partial products until the final result is obtained.
Now let's take an example. Multiply 3 with 2 using 3-bit binary numbers for simplicity. Step 1 is setup. Represent the multiplicand and multiplier in binary. In binary, 3 is represented as 0, 1, 1 and 2 is represented as 0, 1, 0. Initialize the product and the multiplier register. Product P is 0, 0, 0, 3 bits wide. Multiplier register Q is 0, 1, 0, same as the multiplier. Step 2 is to start the algorithm. Determine the number of iterations required based on the bit width of the multiplier. In this case, we will perform 3 iterations since the multiplier is 3 bits wide. Step 3 is iterate. Perform the following steps for each iteration. Check the two least significant bits of the multiplier register Q1 and Q2 to determine the operation to be performed. 0, 0 means no operation, skip to the next iteration. 0, 1 means add the multiplicand to the product, that is P equal to P plus multiplicand. 1, 0 means subtract the multiplicand from the product, P equal to P minus multiplicand. 1, 1 means no operation, skip to the next iteration. Right shift the multiplier register Q and the product P by 1 bit, discarding the least significant bit of the product and shifting in the most significant bit of the multiplier register as the new MSB. Repeat the above steps for remaining iterations. Step 4 is the final result. After the 3 iterations, the product P will hold the final result of the multiplication. In this example, P is equal to 110 in binary, which means 6 in decimal system. So the result of multiplying 3 with 2 using Booth's algorithm is 6.
Advantages. Booth's algorithm reduces the number of practical products that need to be added compared to the basic multiplication algorithm, which results in faster multiplication. Second point. Booth's algorithm is well suited for hardware implementation, as it can be implemented efficiently, effectively, using shift and add subtract operations. Third point. Booth's algorithm can handle signed integers effectively, as it uses signed digit representation of the multiplier, allowing for easy handling of positive and negative numbers. Conclusion. Booth's algorithm is widely used for techniques for signed integer multiplication that improves the efficiency of the multiplication process. By using a signed digit representation of the multiplier and optimizing the generation of practical products, Booth algorithm reduce the number of steps and operations required, making it an effective method for signed integer multiplication in both software and hardware implementations. Thank you everyone for listening to us.